Hello and welcome. Today I'm going to show you how to run the bin microphysics model lots of times to run it in a so-called batch configuration so you can get lots of insight into the things that the model is sensitive to. In order to do this, it's best to run the model from the Spider interface, which you should have installed already and set up. If not, there's another video showing you how to do that on my YouTube channel. So in order to run the model lots of times, go to Spider and open up the batch runs py script, and also open up the runs define script. Now I'm just going to explain the runs define script because there are several variables in here that are important to the setup. So the first one is the output directory, where the files are going to be written to. That's in /temp. And this runs to do shows us it's a list of simulations, and here we have a list of 6 types of simulations: 1, 2, 3, 4, 5, 6, and each type of simulation has 2 possible values. So the first one, W in it, that's for the vertical wind. That's how fast the air is moving upwards in the parcel of air that we're simulating. So that goes from 0.6 meters per second to 6 meters per second. Second, we have the initial temperature, which is initially 244 Kelvin and then finally 200 Kelvin. So very different temperatures there. Here we have the initial relative humidity, so one starting at 95%, the other starting at 75%. And then we have different properties of the aerosol. So this is the number in 3 different modes. You see the second one here has this third mode set to 60 times 10 to the 6 instead of 460. And here we also have different diameters. So the diameter of the aerosol has this last one changed, going from 1.36 times 10 to the minus 7 to 2.36. And the final one is sigma aerosol, which is how broad the distribution is. So D is the diameter, sigma is how broad, and N is how many of the aerosol particles there are. And it's in 3 different modes. So in each case we're only changing the final mode. And then the columns here refer to each type of simulation. So W changing the vertical wind, T changing the temperature, RH changing the relative humidity, N changing the number, D changing diameter, and S changing sigma. So now we're going to go to batch runs, and we're just going to click play. And we'll see that we'll do 64 simulations. And the reason it does 64 simulations is because if we do all different combinations of these simulations, that's 2 to the power of 6, which is 64 simulations. So it looks like that's finished now. So we should have these files on our computer, and we can check that by changing directory to /temp. I've just pressed Command and Shift, and I'm going to type in /temp. And we can see here that we have these different output files now, which are output files from the simulations we've just done. So the next step is to go to factorial method and press play to analyze those results. So that's run very quickly. So now we can see the way to interpret this is to first look at the effects of X, Y, and Z. You see there are 6 rows here of each of the different factors. And the biggest number means that that's the biggest factor. We're looking at the effect that each of these factors has on the total number of ice crystals. That's our metric. Total number of ice crystals in the cloud. So we can see the vertical wind, in changing from a low number, 0.6, to a high number, 6, it has quite a big effect. About 300,000 is the effect. The biggest effect is changing the temperature in this case. So that's 431,000 or so. Positive effect in reducing the temperature. It has a positive effect, so it increases the number of ice crystals. The next factor, which is the relative humidity, actually reduces the number of ice crystals. So if we reduce the humidity from 0.95 to 0.75, we reduce the number of ice crystals by this factor. The next factor is the number. You can see this has a negative effect. That's because we've reduced the number of particles. And diameter has a positive effect. We increase the diameter, we increase the number of particles, but not so large. Changing the breadth of the distribution, sigma, also has a positive effect, but not so much. Another thing that's calculated is this table of interactions. And this table explains how each of the factors within these columns interact with the same factors in each of the rows. Now the rows are numbered, but they correspond to the same factors. So 0 corresponds to W. You can't have the interaction between changing the updraft, W, and itself. So that's labelled as a nan, meaning it's not a number. But you can have an interaction between the temperature, changing the temperature, and the vertical wind, and that's shown here. And that's the same for each of these factors. And the table is also symmetric, you'll notice. So this number here, the interaction between temperature and updraft speed, is the same as the interaction between updraft speed and temperature. So it's a symmetric table. More of that's explained in the paper by Teller and Levine, so I'll leave you to have a look at that in the project. Okay, if you found that useful, don't forget to hit a like and subscribe to my channel, and thank you for listening.